In this episode,
we're talking about the most important physical and chemical properties when considering which meter to use and how to use it.
good stuff.
Hey Bobby, you know what the worst part about arriving on a hazmat scene is?
Besides the fact that I have no hair?
Yeah, but also it's the uncertainty. You don't have any idea what's in the air.
And assuming it's just chemicals doesn't cut it. You need some answers and you need them fast.
And that's where the Explorer comes in. That's real-time chemical ID and quantification right in the field.
It's not just, that's probably not good. It's going to tell you exactly what's there and how much.
And so you can set up safety zones like an adult and not some rookie just guessing, where should we put this tape?
Right. Defensible, quantitative data in seconds makes decision makings. It's a hell of a lot faster.
So there's no more waiting around for an answer, just solid, life-saving intelligence.
Check out Explorer and stop guessing. Check out 908devices.com.
On a hazmat call, the question is never if radiation matters. It's where are you going to find it?
Right. And half the time, I'll say, it finds you first. And that's where unknowns, RAD, is one of the first things that we're going to be looking for.
Because you're not seeing it, you're not smelling it, and if you miss it, it's already in it.
Exactly, which is why teams are checking out Teledyne FLIR Defense's identifinders.
Yeah, and this isn't just a one-size-fits-all tool either. They've got handheld rids, wearable personals, and even backpack systems.
So whether you're the first guy walking into the building or out, it's a bigger picture, and that's something that fits our job.
And these aren't theory tools. These are out there getting used every day by teams that actually rely on radiation data to make decisions.
So if you want to check them out, check out FLIR Identifinder. That's FLIR, F-L-I-R, Identifinder. And we promised we would look into a solution for battery fires, and many companies have presented their stuff to us, and there is one noteworthy one because it actually extinguishes lithium-ion fires. It works on multiple classes of fires, it prevents fires from spreading, and lithium-ion batteries from reigniting.
And before any of you keyboard warriors start caps locking, yelling at us, and asking for proof, the links are in the show notes for UL Class A and B, as well as BSI for 10 categories, including lithium-ion batteries.
Now, we put it through our field tests, and we're impressed by the results, and we suggest that you do your own myth busting. It's available in multiple different types of operations and options to integrate in your current process, and you can access it by checking out the fire suppression solutions or clicking on the link and the show notes below. So, okay, good.
There it is. We're here at Cold Zone. Me and Bobby have the rare privilege of being in the same room, actually.
It's weird.
So yeah, we're gonna record an episode together. We figured why do it over, our normal software when we can just be together.
And this is not our hotel room.
It is a hotel room, but it's not our hotel room. I think that's an important designation.
It is important to say.
So today we're going to be talking about the 5 most important physical and chemical properties when trying to decide how to meter and what to use in our metering operations.
This topic intrigues me because much like everybody likes to say, if you have one chemical and physical properties, this is the one you want. It's like, we were talking about this before, is like I want them all.
Yeah.
But analysis paralysis starts slowing down the operation and getting at some point you have to go and do your thing.
Yeah, and the other thing is that, when you vector in to doing monitoring or metering, like different physical and chemical properties matter opposed to just doing general hazard awareness or something, right?
Right.
Like there's only some of them don't matter at all in terms of my monitor selection, but they matter a ton in terms of what I would expect the scene to play out to be.
Right. Like one that pops in my head is like odor threshold. It really doesn't factor into metering at all. However, it does tell me in an indirect way how my monitor is going to react. And some of the explanations you're going to have to give, the chief's going to say, well, why do I smell gasoline, but your meter's not going off, or something like that. It's well, that's going to have a certain argument for it.
Yeah. The other one I think of is vapor pressure, right? Vapor pressure matters, like it might be the quintessential physical and chemical property, but
Yes.
other than the fact that is there going to be vapor versus not, it doesn't really affect which meter or something I would use that much.
Right, exactly. I would say, and I don't want to put the number one thing I would want to do, but it would definitely be in the top three. I would need to know is like the vapor pressure is like, because it tells me the size of your incident, right? The higher the vapor pressure, the bigger the incident, and the smaller, down to the point where it's a pile of powder, which you can basically put your meter into it and get nothing on it all.
Exactly. But to kick off this list, there's something very similar to vapor pressure, which matters a ton, which is vapor density.
That is a good point. Vapor density, all right, so everybody knows what vapor density is. Where you're going to look, you typically look for the gas or the vapor you expect it to be. How's that?
Yeah, and the nicest fun fact about vapor density is that all but 13 things go down. So when in doubt, look down.
Yeah, it's
right?
a very good bet.
It is a very, very good bet. There's a lot of chemicals and almost all of them go down. But knowing where to look is vitally important to any metering operation, right? You could walk around for the rest of your life with your meter over your head, and if the thing that you're looking for is heavier than atmosphere, you're never going to find anything.
Right. So is that a foolproof answer, right? If we're metering and I expect things to be down, can you save, let's say your career, like you just said, let's say your entire career, you just put the wand on the ground and you drag it like a leash, right? Just drag it on the ground.
Yeah.
You would probably statistically be okay for the vast majority of the incidents. Would you agree?
Yes, I would caveat it though.
Okay.
Here's my counterpoint. The most common incidents we go in the fire service, in hazmat, happen to involve things that are lighter than air. Unfortunately, right? When we think about methane, carbon monoxide, right? These are some of the most, like natural gas and CO are some of the most common, quote unquote, sometimes people don't even consider them hazmat runs because they're so common.
Right.
They happen to both be lighter than air, unfortunately.
They do. They do. But, all right, so then in our, not only operation, but our metering as well, is that things that go up typically handle themselves.
Yes, we like that.
Which is good, right?
Yeah.
But on the other side of that whole thing is that, let's say we have something like propane, which, you can guess it goes down. Can you guarantee propane will be down? And the answer is like hot propane. Why would propane be hot? Because you have heating systems and HVAC. So could propane be up? Mm-hmm. Yeah.
It's not, nothing in hazmat is guaranteed, unfortunately.
Yeah.
And inversely, right, we have something like ammonia, right, which is one of the 13 gases lighter than atmosphere, but oftentimes when it's released, it becomes very cold and it sinks.
Right.
And so you can't trust the reference materials all too often, unfortunately.
I love that because vapor density is one of those things that, especially in the beginning metering stages of your career or monitoring stages, is that people take that as Bible. And I just have to look in this location and it's going to be good. So if I just do this, and we oversimplify our monitoring strategy to these very fire service heavy if-then statements.
Mm-hmm. Yes. We like simplification, but also, unfortunately, nearly all of hazmat is nuanced.
Yeah,
right?
It is. And that's it's more of a thinking sport. Like, that's where that whole it depends comes in.
Always it depends.
It brings this whole nuanced thing of like, look at all the complexities I understand, and it's like, yeah, I get it, but vapor density is one of those ones where it definitely does depend, because things like humidity would push down things more, or influence temperature gradients, density, and I mean actual density, like what's my elevation. Would change that, right? Then we get into like partial pressures and all the other stuff. And
it can get way complicated. And we could probably talk about this for the entire episode, but we do need to get through all 5.
Yes.
Right? So I'm sure there's plenty of time for us to come back and break down vapor density in way more things, but we'll move on for now.
Yes.
The next one I want to talk about.
Go.
Flashpoint.
Okay.
The reason I bring up flashpoint is this. We know that we're looking for flammability or combustible gases with our CGI or LEL sensor. That flashpoint will very often help us know how sensitive that catalytic bead sensor will be to a given commodity, right? Okay. So we know how accurate it will be. Say we calibrate to methane, but we're looking for diesel vapors or some other thing that reacts very differently to that sensor. Understanding its flashpoint and where it falls inside that spectrum will help us know how sensitive we should expect that to be for this.
It's also commodity. It's directly tied to vapor pressure, right? So your boiling point, your flash point, and your vapor pressure speak very similar. Those are three big terms you'll hear guys talk about, and they're tied together. They're not the same thing. There is some nuance to what each one means to you in response. Like my flash point, if I'm thinking about it from like the tech ref point of view, I'm thinking about flash point as possibly more of an indicator of my PPE selection. In addition to your metering, right?
Yeah.
Your boiling point is probably gonna be tied more to my metering selection. And then your vapor pressure is more of I don't wanna say, it's more of like how big my scene is. You know, where do I expect my prediction modeling? Because if I have a meter and I'm getting a reading, I'm going for something that has a low vapor pressure, but I'm getting a reading from 10 feet away, I would have to be like, maybe this isn't what I'm thinking it is. It could be a different dog. So I think those three, and I know we're only speaking about, flashpoint. But those three, I think, are common parlance in discussions. And if you, whoever is listening to this, get that chance, just tease that out. Like go to the firehouse or the police station or wherever you're going to, and look up the three and have an open discussion about what the three mean to your team. Yeah,
and to tie back into that, as we can talk about flammability, and we tie in flammability to vapor pressure, right? Vapor pressure means that we're producing more vapors, which means there's more flammable vapors, which means we're getting to our flammability point more readily, which is exactly how it ties to flashpoint, right? The more vapor production, the more easily we can get to our LEL.
I like that.
Which is our next.
LEL. This one is a huge one. Yeah, LEL. I like LEL because I don't want to blow up.
I don't want to blow up either.
I don't want to blow up. But it's one of the hazards that we deal with, right? So if you think about your metering profile in a THMG high level kind of thing, I want to know about toxic, right? Whether something's going to hurt me. I want to know about asphyxiation. I want to know about, but flammability is one of those things that's going to pick your PPE, and it's going to tell you on your metering strategy how far back you can safely be. I would say that's true.
I think that's so. I'll go with that.
Yeah. I think so. But LEL tells me a lot about my PPE.
Yeah. Oh, for sure. I mean, fundamentally, arriving on scene, we're making a decision. Are we in plastics or are we in turnouts, right? We have to decide, are we dealing with a chemical problem or are we dealing with a flammability problem or a toxicity problem versus a flammability problem? Because barring our ability to change our environment, which is obviously our number one priority to make the environment better for us in terms of PPE, but we have to make a choice whether we're protecting ourselves from a toxicity or a corrosive hazard versus are we going to catch on fire. And so I want to break this down one more layer deeper because the nerds out there want the nerdiness, right? So let's go there. I'm going to bring up a scary science word that all too often is forgotten inside of the fire service and hazmat.
Okay.
Stoichiometry.
Oh my God.
So this is the interface between flammability and the oxygen in the atmosphere. Break it down to me.
All right. So it's basically in a very high level. So the super nerds out there, don't start caps lock asking for answers on this thing. But it's basically the idea that the room can only hold 100%. Right, so if this room is 100% air, well then there is 0% contaminants. And as we start adding in, let's say 5% of methane, that means that it can only be 95% air. And so there's a balance, and actually that's a very binary balance. It's an X and Y, but in reality it's a triangle, right? So that you can have, air, you can have nitrogen, and you can have your contaminant coming in from different angles. And as those proportionalities change, your chemical and physical properties and your expectations, your prediction modeling, all changes as well.
Yeah, so when we think about that in terms of, the very standard methane, right? 5 to 15%, right? That is at standard temperature and pressure, right? That's not in every single oxygen environment, right? As we decrease our oxygen, right? Now we go back to, it's not flammable at all. That's kind of how like a halon system would work, right? On the other side, if we increase our oxygen, now our flammable range gets wider and wider and wider, and shit just starts catching on fire.
Right, but as you increase the oxygen, you can't have a room that 110%. Right, so you must decrease now your contaminant, which is, let's say, methane or whatever it is, and that would then change all of your parameters again. And to get more into this, we have to, but first.
Today's episode is brought to you by Rigaku Analytical Devices, who are the folks who've been perfecting the 1064 nanometer Raman longer than some of you have been doing hazmat.
They just launched the 4th generation handheld analyzer, which is the Icon X, and is built specifically for real-world stuff hazmat teams deal with every day. We're talking about dirty powders, mixed materials, dyes, colors, all the stuff that makes other instruments throw a tantrum.
The 1064 nanometer laser means reduced fluorescence, so you get fast, reliable chemical icons in under a minute, instead of staring at a blank screen wondering what the hell is going on.
And this new platform isn't just an upgrade. It's a whole new toolbox. It supports new accessories, including standoff analysis, so you can get to the answers without getting too close.
If you want an analyzer that's been evolving alongside the hazmat world, check out Rigaku's newest Raman at rigakuanalytical.com. Hey Bobby, you know what I love about the city?
People getting shoved in front of the subway?
Ooh, no. It's actually the scooter gangs.
Oh yeah. It's like hazmat with mopeds.
Oh, yeah, and that's where the Ovexian FR saves the day.
Right, lightweight, mobile-friendly, designed for first responders, because the last thing we need is extra weight when things are heating up.
And it's third-party tested to lower toxic gases below IDLH levels.
So you can actually breathe while putting the scooter fire out.
And if you need more, Ovexian FR comes by the pallet load and in certified polydrum kits.
Which is exactly what you need when you say we're going to need a lot of this stuff.
So protect your team and protect your lungs. To learn more, go to hazmatguys.dgo.com. That's hazmatguys.dgo.com.
Okay, so
And we're back. Hi.
So for stoichiometry, as you do a little bit more of this thing, right? You have. I use an example of this. Like, if I threw a candle in a cup of water, what do you expect the candle to do? It's going to float, because wax floats. But if you put it in a cup of alcohol, well, now the candle sinks. And so a lot of this is about the context, right? So when you're doing your metering, your monitoring, and these chemical and physical properties, this is where the it depends comes into the thing, because it's not a simple if this then that statement. It's a lot of contextual, reading the room. So if you're doing your LEL stuff, it also is like, well, okay, what kind of a room, what kind of an atmosphere am I in? And how does my meter interact with it? For example, if I go into an LEL, and let's say my oxygen level is like 15%, how dependable is my LEL sensor at this point? Right? It's suspect, as they say.
Yes, at best, yeah.
Right? So your environment, the atmosphere in general, is going to be very dependent. Your meter readings are going to be dependent on your atmosphere in general.
Okay, so I'm going to pose you another question.
Go.
In this same vein, but I had this question asked to me a couple weeks ago, and I was like, I don't have a great answer for it. I think maybe. I worked my way to it, but I'm interested to get your take on it. So then someone said, if we really don't operate inside the flammable range, why do I care that much about the UEL, and why would I ever want to measure in percent by volume?
That's a good question.
Because sometimes meters are selling themselves as, oh, you don't just measure to 100% of the LEL, you can also measure percent by volume all the way up past the flammable range.
Right.
Why does that matter, or why is that operationally relevant?
I don't know. You know what? Like, because I get it. Like, there's been instances where it has been 100% natural gas, let's say, in an area, and as we open it and vent it and we start bringing it through, it's going through the the flammable range. And one of the things is let's say, for sake of theory, I am standing below the LEL with a flamethrower on my back. Do we have a problem? No, we don't, because we're below the ratio. What if I'm in the flammable range with absolutely no ignition sources? Can I operate?
Yes.
You can.
Yeah. You don't just go on fire, right?
Yeah, you got to be kind of careful with it. But the point is like, if I'm above the UEL, I can again be standing there with the flamethrower. So it's about the perspective of the whole thing. You're metering and you're monitoring. I love the intrinsic safety and everything, but one of the things is we are not intrinsically safe.
Yes.
So, yeah, I don't know. I mean, if you're above, I don't know. I really wouldn't change anything. Would I ever get to a point where I'm above the UEL? There might be.
Other than knowing that it's there, right? But I mean, it does.
Right.
The argument that I played back to this person when they asked why I would care about the wideness of a flammable range is like, so say we did get to that environment where it is 100% charged in this flammable commodity, right? When we have to, inevitably we have to work our way back through the flammable range through ventilation to get back to normal baseline and being able to operate in this area again. That flammable range, how wide it is, tells me how long this is going to be a problem as we move through this. If it's a super narrow flammable range, we're going to ventilate and we're going to have a really dangerous area for a minute or two. If we have something like acetylene where it's 2 to 98, 99%, the whole ventilation operation is a bomb, right? So like that's kind of where I came to that. That would be why it matters. I don't know if I would ever be in a circumstance where I'm like, I need to know the percent by volume of this. Yeah, I don't know, but.
If I had my way, I would want a flammable range that's narrow and high.
Yeah, of course. Yeah, hard to get to and very narrow. Right.
I like that.
All right, let's talk about one that's very specific. IP, ionization potential.
Yes, IP is the amount of energy you need to impart on a molecule or compound to excite it and ionize it. Right.
By that he means to kick loose an electron.
Right. Exactly. And then eventually it recombines. Right. So all the ones that this really sings for is the PID or the FID if you have one of those. But basically you're just splitting off an electron pretty much. And that if you can do that, then the meter can see it. So why do I give a shit about IPs? Because it's a sorting mechanism. Right? That's the easiest way I could say it. It's like, it's if I can do this, well, then I can put everything that I can do it to on this side of the wall, and I can put everything I can't do it to on this side of the wall, and therefore I can get to my answer. It's a crude way of doing it. It's a really crude way of sorting, but it works. Yeah,
and also we arrive on scene, especially when you're thinking about multiple chemical incidents, multiple commodity incidents, and you say, I'm going down range, I'm getting a hit. If I get a hit, like we haven't talked about it yet, but you have a 10.6 electron volt bulb inside your photoionization detector. Below 10.6 we see, above 10.6 we do not see. That there's some very small variations to that rule, but universally pretty much. And so just like Bobby said, we divide the class, right? We see this, we see it, so we know it's below 10.6. Everything that's above 10.6, it's no longer a consideration in this unknown equation. And so, that is the biggest thing is, if I'm gonna look at my tool cache on my rig and say, which meter should I be grabbing? If I know for certain that the commodity I'm looking for has an ionization potential greater than 10.6, leave the PID on the truck, it's just extra weight.
Right. I don't know. All right, I'm gonna push back on that.
Okay.
Because I would still bring it, because if my PID does go off,
then you know it's not the thing.
It could be not the thing or a second thing.
That's a good point.
Like the amount of times that I went to incidents where it was not a single commodity kind of thing, and you're like, wait a second, that doesn't make sense. And then when you start opening up the your eyes a little bit and you say, oh, it's just because there's a little leak of this that they didn't even know about because they don't have the sensing technology or its capability of metering for it. And it was just like a little, we weren't there for it. And yet we tripped across it because something was like, wait a second, why am I getting corrosive in air or whatever the variable was? And it kind of like, if we didn't have it, we wouldn't know it.
Yeah, and that, that is another thing that's nice about it is that, if you think about the actual sensor technology, the PID is one of the fastest to respond of all your sensors, right?
Yeah.
Faster than electrochemical, right? Faster than cat bead. So if you're thinking about like a 5-gas meter, you're going down range, if it's going to hit on these things, theoretically, it should hit on your PID before it hits on the other things. So you're going to have a little bit earlier indication of a problem.
With a incredible resolution.
Yeah, we're down to, like, I think you can get to 0.1, which would be, 100 parts per billion. Yeah, very small. And so let's layer one more thing in. We've kind of covered how we would use the physical and chemical properties, but I want to talk about technique a little bit more, because I think that all too often when we think, if we go back to the very beginning, if we think about vapor density, we think about this idea of slightly raising your hand over your head or kind of lowering your hand to your waist. Talk to me about the experience you had working and where these meters actually needed to be to find things.
Right. I will say, your vapor density is going to is your prediction where I'm going to put my meter, and I will tell you that I have found propane on the ceiling. I have found butane on the ceiling. I have found helium on the floor, and the reason is because of temperature gradients and stuff like that. That usually pushes things around. So when I am, and this is kind of like melding in a couple different things, is that if you're metering for a reason, right? You were cold there for a problem or whatever it is. Part of that whole thing is slowing down your approach, right? It's 1 second up, 1 second middle, 1 second down, and down is touch the floor, like tap it to the ground kind of thing. And then 1 second step. Because if you look at these T90 times and some of these meters and stuff like that, depending on your make and model and that kind of jazz, some of them don't put an accurate number for 60 seconds, which is a significant amount of time, right? So if we were to drop the mics right now and walk, we could probably get downstairs. That's how far you can go.
Yeah, and that could be a very big problem if you're walking through an unknown environment, right? Yeah. You don't want to figure out that you have a problem and then have that problem be, half a block away, right?
Yeah. So it's a lot. There's a lot of different dynamics and things that feed into it. And again, we set this up in the beginning, is that these 5 are, I would say, mission critical.
Yeah.
I would say, and are you going to get all 5 of those every single incident? More than likely, no. No.
But so this is the thing. When you're making metering selection, you need to be making a plan first and then proving or disproving your theory. Like this, we should be looking at metering as the scientific method. I've arrived on scene. I've looked at my physical and chemical properties. I'm going to go down range and figure out if what I believe to be true is true or false. When I go down range, I discover whether I'm correct or incorrect, and then I adjust accordingly. Either I walk down range and say, oh, I expected to find flammability and a hit on my PID. Sure enough, that's exactly what I got. That's awesome. Or you go down range and say, the commodity I'm looking for has an ionization potential greater than 10.6. I go down range and I get a hit on my PID and go, oh shit, what we thought we had, we don't. But it has to be that way. You can't be the person that walks down range and waits for the beeps and the blinks.
Yeah.
You have to have a plan and then prove or disprove that plan while you do your metering operation.